Okay, hi everybody. My name is Cho. I'm a faculty in UC Davis, and today I'm going to present our paper on developing a new distributed training algorithm for kernel machines, including kernel SVM and kernel logistic regression. This is joint work with Hsieh in Google Research and Industry Dylan in UT Austin and Amazon. So the outline today, I will first give some background. Basically, I'll answer what is kernel SVM and why do we want to parallelize it. And then I'll describe our algorithm and then show some experimental results. So some background about support vector machine. In this talk, we basically consider the binary classification problem, but everything can be extended to multi-class. So in the binary classification problem, we have a training data x1 to xn. Each xi is a d-dimensional feature vector, and each of them are associated with label yi belong to positive 1 or negative 1. So not many people are using linear SVM. So what linear SVM do is you want to, so given data from two classes, you want to find a linear hyperplane to separate these two classes. And in the prediction phase, you can use this hyperplane to do the prediction. So basically, you want to split in Euclidean space. So you want to find the vector W to minimize the regression term plus the classification loss. So this is basically the objective function for linear SVM. But in this case, you are very lucky. Your data is linearly separable. You can find a very good separating hyperplane to split two classes of data. But in many real cases, you cannot have a good linear hyperplane. For example, in this very famous XOR dataset, you have data from two classes in a two-dimensional space like this, and you can never find a linear hyperplane to get good prediction or training accuracy. So in this case, a classical approach is to use kernel method. In kernel method, you try to map the data to a higher dimensional space, and you expect if you map to very high or infinite dimensional space, data will become linearly separable. So in this case, you can use this very simple nonlinear mapping to map x to phi x to a three-dimensional space, and then it will become linearly separable in the three-dimensional space. But in many other problems, you don't know which mapping you want to use. So typically, we map to infinite dimensional space, and it's called kernel SVM. So the only difference between linear SVM and kernel SVM is you need to have a nonlinear mapping phi of xi for each training data point. So this will map your xi to a high dimensional, infinite dimensional vector. And in this case, the primal problem will become very hard to solve because, for example, if phi xi is an infinite dimensional vector, then the primal w is also an infinite dimensional vector, and you cannot directly solve this optimization problem. So in this case, people usually transform to a dual problem and then solve the dual formulation. In a dual problem, when you transform the primal to a dual problem, each dual variable alpha I corresponds to one training data in the primal space. So you have n training data, then you have n dual variables in the dual problem. And the dual problem here is actually a very simple quadratic minimization problem with bounded constraints. And the only difficult term here is the Q matrix, which is a n by n matrix, and Qij is defined by Yij multiplied with inner product of phi xi and phi xj. So the good thing about the dual problem, firstly, the number of variables, you have n variables, no matter how large the dimension you want to map, you only need to solve a problem with n variables. And another good thing is you don't need to explicitly define your nonlinear mapping here. So the only thing you need to do is you only need in a dual problem is define the Q matrix, and Q matrix only related to the inner product phi xi and phi xj. So the only thing you need to define is the inner product of 2 points in the high dimensional space. We call this a kernel function. So kxi equal to the inner product, and you only need to define this kernel function instead of the high dimensional mapping. And after solving the dual problem, you can use this primal dual relationship to get the primal solution and use it to do the prediction. So typically in kernel SVM, many people are using Gaussian kernel, and sometimes in some like natural language processing application, you also want to use polynomial kernel. And the challenge is, in the worst case, if you want to solve this conjunctive minimization problem, your Q matrix is an n by n dense matrix, which require n square storage. And the time for solving a conjunctive minimization problem in worst case is n cube, which is very large because n is a number of training data. If you have millions of training data, then you will take forever to solve this problem. Of course, there are some tricks to speed up this, so it's still solvable, but it's very slow. So let's try to answer the question, why do we still want to use kernel SVM if we have linear SVM? On the one hand, we have linear SVM. On the other hand, we have deep learning. But I want to use this dataset to show kernel SVM still have some advantage on some datasets. So we do experiments on this UCI cover type dataset. So basically, you are given the features for this cover, and you want to predict the cover type. So in this dataset, if you use linear SVM, then you can only get 76% accuracy, which is very bad. It's a binary classification problem. So this means the data is not linearly separable. And if you use kernel SVM, you can improve a lot. You can get 96% accuracy. So basically, you almost can get a correct prediction. But on the other hand, if you consider training time, linear SVM, you only need 10 seconds, less than 10 seconds to solve the problem. But if you go to kernel SVM, using Gaussian kernel, you need 15 hours to solve the problem. So you get better accuracy, but okay. So you get much better accuracy, but you also encounter much longer training time. And I also list the accuracy for deep learning on this dataset here. So if you use 3 hidden layers, this is the tutorial in, I think, H2O package, and you can get 85% accuracy. And we also try to increase to, so in deep learning, typically you want to add more and more layers. You should get better accuracy. So we increase to 15 hidden layers, and you still only get 91% accuracy. It's still worse than kernel SVM. So this shows, although deep learning is very good for some datasets, there are still some other datasets, kernel SVM will get better accuracy. So in this talk, basically I have given all the background. So in this talk, our focus is how to speed up the training for kernel SVM using a distributive system. So our result, we can reduce the least 15 hours to 2 minutes using 32 machines, each one with 20 cores. So basically, if you can train an algorithm in 2 minutes, then you can very easily select the hyperparameters and get very good performance. So now let's discuss how do we do this in the distributive system. So in the our focus is solving this dual SVM problem. You have a conjunctive minimization problem with boundary constraint. You have n variables, and each variable corresponds to one training data. So the main idea is very simple. We just try to partition the variables into k parts if you have k machines. So each machine only updates the variable for one subset. So we partition 1 to n, the index set 1 to n. You have n dual variables. So we partition this set into k non-overlapping subsets. And the ith worker only updates on the variable si. And so they are doing independent updates. And after several updates, maybe thousands of updates, they try to synchronize to get the next iterate alpha. So this is an illustration for our algorithm. Assume you have 3 workers. So initially, all the workers share the same global parameter alpha. And now each worker try to update a subset of variables independently. So worker SR will try to minimize this objective function by updating the alpha, the subset SR of the dual variable alpha. So you try to find the best solution, best direction to update the subset of the dual variables here. And DSR is the direction you get. So the first worker try to update the first part of the variable. Second worker try to update the second part of variable, and so on and so forth. And so there are no communication here. Every worker are doing this independently. And then after a while, we try to gather all the updates to get a global update vector D. So D is a concatenation of DS1, DS2 to DSK. And then so if you direct add D into your solution alpha, then your algorithm will diverge. Later we will discuss the detail. But in this, when we synchronize, we need to add the step size beta and then update our parameter alpha by alpha plus beta D. D is the direction, beta is a scalar, is a constant. So our algorithm, the main contribution of this work is we find there's a way to compute the optimal step size beta here by minimizing the SVM objective function. So no matter how bad is your update direction D here, you can always find a optimal step size beta to reduce your objective function value, and this can be done very efficiently. So later I will discuss this. So this is the algorithm sketch. In the first step, every local worker try to do the local updates in parallel. So each of them try to solve this local problem. So I try to update alpha to alpha plus delta alpha SR and try to minimize the objective function value. And then in step 2 and step 3, they communicate to get the global direction D, and then try to find the optimal step size beta, and then update the dual variable by alpha plus beta D. So let's discuss each step in detail. The first step is local updates. So actually local update is very easy because if you plug in this into the original SVM objective function, you will see the resulting subproblem is a smaller quadratic minimization problem, and the size is corresponding to a number of variable in this partition. So delta SR is the subset of the dual variable. QSR is the diagonal block of that kernel matrix. And so the only difference between this one and the original kernel SVM problem is this linear term. So originally the linear term is -1, but now you add some information, add some Q alpha I to this. So typically, so you can use any existing kernel SVM solver. For example, in our experiment, we use libSVM to solve the local problem. And later we also show in the theory we can show that you don't need to solve this subproblem exactly. So in distributed optimization, typically you want to do some local updates and then you want to do some global updates. So we show you just need to solve this exactly in order to get the convergence, linear convergence. Okay, and the second step is very simple. You just gather all the direction to get the global direction. And the third step is the main contribution here. We want to see how to compute the step size beta exactly. So f of alpha plus d may not decrease the objective function value because in the first step, in the individual independent update stage, everybody are doing the updates for their own variable, but they don't see the update from other computers. So there might be confliction between different updates, and this will cause your objective function even increase. So you cannot use step size equal to 1. And all the previous work, including Cocoa and Cocoa Plus, they are algorithms for linear SVN, distributed linear SVN solver. They are trying to update the parameter by constant times d, and you try to tune the parameter eta here. So there are two drawbacks. First, it's tricky how to choose the parameter, because if the eta, the step size is too small, then your convergence is very slow. If it's too large, then your algorithm diverges. So there's you need to tune this pretty well in practice. But in distributed system, I just want to solve the problem using multiple machines. If there's an additional parameter to tune, then you may spend even more time to find this parameter. So another drawback is you can, if you just use a fixed step size, then you cannot automatically adjust the step size dynamically during your process. Maybe in the beginning you want to use a smaller step size, and in the end you want to use a larger step size. So you cannot do this in previous work. Our goal is to automatically choose the step size which can be computed efficiently and guarantee fast convergence, linear convergence. So actually it's very simple. If you try to solve this optimal step size, I want to find optimal beta to minimize the objective function. In this case, if you write down the objective function, here is the detail, but let's go to the second line. So you'll see this function is actually a constant plus this term is linear on beta, this term is quadratic on beta, this term is linear on beta. So this is a quadratic function on beta, and you have a boundary constraint here. So basically, it's a one variable quadratic function with boundary constraint, and you can easily compute the optimal closed form solution here. And you can use this. So you only need order 1 communication to get this step size, and it's optimal. So this is the main technique we use in our algorithm. And we show the convergence rate. First, we assume if the objective function is strongly convex and each subproblem is solved by coordinate descent or gradient descent with at least 1 iteration. So you can solve a fixed iteration or a constant iteration. So we just require you solve it more than 1 iteration. Then you have a linear convergence rate. So here, this means every iteration you can reduce the objective value by a linear rate. And we also extend our algorithm. Actually, this theory holds for any subproblem solver if the subproblem solver can reduce the objective function linearly. So basically, coordinate descent or gradient descent can reduce objective function linearly, but you can replace this by other solver as long as you show they can reduce the function linearly. For example, SVRG or any variance reduction technique can be used. And second, we extend this to some non-strongly convex function. For example, there's a condition called global error bound. We show if the function satisfies global error bound, then you still have linear convergence. Basically, many functions satisfy this condition, including SVN with linear kernel or any polynomial kernel. So finally, we try to discuss how do we partition the data or the dual variable. So I didn't mention this in the algorithm. Basically, you can do it randomly, but we show there's a better way to do it. So the descent direction we compute, the d vector here, is actually, if you do some derivation, you can see it's equivalent to the minimizer of this approximate function, and the approximation is done in the second order term. So originally, the second order term is the Q matrix, the kernel matrix. But if you try to do the distributive update, then it's equivalent to solving another function where the kernel is replaced by this block diagonal kernel. So you try to set every term between the different parts of your variable are set to 0. So you only keep the diagonal blocks here. And so the algorithm, the convergence speed is related to the approximation you done here. So you approximate your Q by Q bar. So as long as your Q bar is very close to original kernel matrix Q, you will get fast convergence. So we show that if you use k-means or kernel k-means to partition the data, then you can get much smaller approximation second order term compared to random partition. And this is an experimental result showing that using k-means partition, the blue curve and the red curve is much better than this purple using random partition. So the difference is very huge. So if you use our algorithm, don't use random partition, use k-means partition. The experimental results. So first we show the compared distributed kernel SVN solver, PPEC SVN and PSVN. We are much faster than them. So we can get a very accurate solution in maybe several minutes. And if you just want an approximate solution, we can do it in several seconds. And then this is a figure we compare with RFF, random Fourier forest. So you can use RFF or nice strong approximation to kernel and then use OpenMP live linear to solve it. And we are still better than those algorithms. And finally, we have OpenMP plus MPI hybrid implementation. So you can use distributed system. You can also use the multi-cores in each machine. And this is the speed up. So basically, the x-axis is seconds multiplied with number of cores. And the y-axis is the objective function. So if the curve overlap, then you get exactly linear speed up. So the curve is almost overlap, which means we almost have a linear speed up using multiple machines. So in summary, we have a distributed kernel SVN solver. It is very quick and easy to use, and you can use distributed and multi-core in each machine. The source code is here. And also, if you don't have multiple machines, you only have one single machine with multiple cores, you can use our recent work on asynchronous kernel SVN solver in NIPS last year. Okay, thank you very much.